All right, I've got a polynomial written out here. It's a fifth degree polynomial, so that means it might have up to 5 linear factors, and that's a lot. Or it might have like 4 and one of them is multiplicity 2. That's what's actually going to happen. I've got one more piece of technology because this guy's going to have a really long list of rational roots. There's a theorem called the upper and lower bound theorem, and I'll just show it to you as it becomes relevant in this problem. But it basically answers the question, hey, am I out in the end behavior? So basically, if I'm testing the number 4 and I find out I'm out in the end behavior, if 4 is in the end behavior, then obviously so is 5 and 6 and 7. So if those are on my list of rational roots, I can cross them all right off. I'm already too high at 4, so these would be way too high. That's what the upper and lower bound theorem does for us. So I'll show you how to apply that as it becomes relevant. But until it does, let me scooch this off. Until it does become relevant, we're just going to solve this problem normal. So here's the process of solving one of these problems. We're going to try to apply all our technology. So we're going to look at the formula. The constant term is going to tell us the y-intercept. So I know this thing has a y-intercept of 20, 0, 20. That'll come in handy. The leading term is going to tell us about the end behavior, 2x to the fifth. So it's going to go up to the right and down to the left, and it's going to have this point, 0, 20. That's what I know so far. Constant term, leading term. I can look at the sign changes. So let's see, we got 1, 2. So we have 2 or 0 positive roots. Good to know. I mean, it's a fifth power, so the fact that I've only got 2 or 0 positive roots, that narrows things down. Once I find 2, I'm done with positive roots. That'll come in handy later. And then let me see, f of negative x is negative 2x to the fifth, and then x to the fourth stays positive. 9x squared stays positive. Negative 32x goes positive, and 20 stays positive. So now there's only one sign change. Whoops, and it's not there. One sign change from here to here. So we have exactly one negative root. No more, no less. That's a pretty handy result. So I pulled out, so I looked at DROS, I looked at the constant term, and I looked at the leading term to get me all of this information. So I'm gathering intel before I go into the fray. Now I need to get a hit list of targets for my synthetic division, and that list is going to come from the rational roots theorem. I'm going to be dividing by a 1 or a 2. And my numerator is 1, 2, 4, 5, 10, or 20. Now, a few of these will be redundant, like 2 over 2 is 1, 4 over 2 is 2, 10 over 2 is 5, 20 over 2 is 10. So my list works out to be, all of these could be positive or negative, and they could be 1, 2, 4, 5, 10, or 20. And the only things I need to add to that list, if it'll show up on the, okay. Only things I need to add are 1/2 and 5/2. So I've got a list of 16 numbers, 8 positive and 8 negative. There we go, 8 positive and 8 negative. Those are all the numbers I can test. So the only thing we haven't seen yet is the ULB, and I'm about to show you how that looks. Let's say I say, maybe 2 is a root. 2's on the list, it could be a root. Let me copy the coefficients. What does it go? 2, 1, 9, negative 32, 20. What's the mistake? Pause the video until you can tell me what the mistake. No, I'm just kidding. I mean, you don't have to, but well, I'm going to tell you now. There's an x cubed missing. So my coefficients are 2, 1, 0, 9, negative 32, and 20. Without that 0, the rest of this problem does not work, and we spend 40 minutes doing nothing. Yeah, like I said, this entire video is one problem, so it's going to be a beast. We'll see how long this takes us. Let me stop jib-jabbing and get to it. 2 comes down. 2 times 2 is 4. Add for 5. Multiply for 10. Add for 10. Multiply for 20. Okay. So like before, you multiply by the c, you multiply by 2 to go up, and you add to go down. 0 plus 10 is 10, 9 plus 20 is 29. Sometimes people think it's subtracting. I don't know why. It's adding. So here's our answer. Now, I'm not going to write out the polynomial or anything. No, I want to point out something far more interesting. 1, this is not a 0, so 2 is not a root. But 2, we have something amazing here. 2 is a positive number, and the entire bottom row, including the remainder, is positive. When that happens, when this number and all of these numbers are positive, it's because you've picked a root in the right end behavior. So let me draw a scoreboard here. Here's what I'm going to do. I'm going to take this possible list of rational roots, copy it. There we go. Paste it. Paste it again. Okay. So this is the list of all 16 possible rational roots, yeah? Well, 2 doesn't work. I know 2 doesn't work because the remainder is 72, but I know something way cooler than that. What I know is that 2 is an upper bound, so if 2 is in the right end behavior, then anything bigger than 2 is also in the right end behavior past all the zeros. So that means 4, 5, 10, 20, and 2.5, not 1/2, but 2.5. Those roots are all too big. So I did 1 synthetic division, I killed 6 roots. Or, well, 6 potential roots off of the list. Now there's 10 potential roots remaining. I'm going to copy that for later. All right, so 2 doesn't work. I'm going to go ahead and try negative roots for a bit. Let's see if -2 is a root. Well, this part, you get faster at it. See if you can follow along with me on your own sheet. 2 comes down, and then you multiply to go up, and you add to go down. Oh, whoops. This should be negative, this should be positive. And that means this number, update the screen. Yeah, this should be negative, that should be positive, and that means this number is actually a -26, multiply for 52, and add for 72. Actually, the same remainder as before. Weird coincidence. And that's all. It's just a weird coincidence. So all that means is that, God damn it. No. God, no. I'm swiping with 3 fingers, you stupid iPad. This is terrible. My hands get sweaty and then gestures stop working. I'm cursed, I tell you. All right, you copy. And now, no. What? Come on! Oh my freaking God. Okay, it's not. Yeah, you know what I'm gonna do? I'm gonna take the scoreboard with me. Take my ball and go home. Okay. At this point, all we can say is -2 isn't a root. There's no cool pattern here. It goes negative, positive, negative, positive, negative, negative, positive. That's not that exciting. So I just know that -2 isn't a root. Okay. No, you know what? Why do they have to change the gestures every time iOS updates? I swear. I really want a copy of this thing. No, no. Okay. This good guy gets copied. And then hey! 1 in 10 times, it works every time. What do you know? And I swear, I did the same thing each of those freaking times. Okay. So now the -2 goes. Now we've got a slightly better board. Let me try a bigger negative number. Let's see if I can land in the left end behavior and show you what that looks like. I'm going to try -4. 2, 1, 0, 9, minus 32, 20. 2 comes down, multiply, -8, add, -7, multiply, 28. Add, 28, multiply, -112, add, -103, multiply, 412, add, 380, multiply, -1520, add, -1500 exactly. So you notice how when you get a real bound, like up here, not only are they all positive, they just kind of balloon out of control more or less. And the same thing's happening here. They're alternating rapidly between positive and negative and just ballooning out of control. They're going wild. So when this guy is negative and these guys have sign changes every time, so there's no double negative like there was up here. It's just nothing but sign changes. Then what I just found out is that's the pattern that lets us know that no matter what happens in the middle, -4 is a lower bound. Okay, wish me luck. I'm going to try to paste. Fuck. Trying again. Copy. Yeah, I swear that's it. I did the same thing twice. So -4 is a lower bound. And anything to the left of -4 is also out. So that's -5, -10, and -20. Gone. All of them. So we just killed another 4 numbers with one synthetic problem. So the pattern for an upper bound is this guy and all of these guys are positive. For a lower bound, it's this guy's negative and these guys alternate. Okay? So we've got 5 roots that we could have left. 1, 1/2, -1, -1/2, and -5/2. All right, let's try 1. I still haven't pulled any roots out. It's still a 5th degree. 2 comes down. 2 times 1 is 2. 3, 3. Dividing by 1 is really fun. Because the multiplication step is very, very simple. You just copy the number. And would you look at that? Hey, we found a root. We found a root. 1 is a root. And we're left with 2x to the fourth and 3x cubed and 3x squared and 12x and negative 20. Now, if you remember back in the before times when we started this problem, I said there were either 0 or 2 positive roots. We just found our first positive root. There has to be a second positive root. And it either has to be one, that positive root has to be either 1/2 or 1. Those are the only 2 positive roots it could be. It could be 1 again. Now here's the thing. I knew this was going to be 1 because 2 plus 1 plus 9 plus 20 minus 32 is 0. In other words, when you plug in a 1, that's the same as adding up the coefficients. Add them up, get 0. Well, 1's going to give you a 0. Do you see why? Because this polynomial is scrolling. When I plug in 1, I just get 2 times 1 plus 9 times 1 minus 32 times 1 plus 20. So when I plug in a 1, I just get the sum of the coefficients. Now my new polynomial has coefficients 2, 3, 3, 12, and negative 20. Those add up to 0 again. So I'm going to plug in another 1. And now here's a fun trick you can play. I'm going to put my box right here and use this as the first row of my next synthetic division. Like so. Just cut those off. Well, this is the result. I don't want to copy that down. So 2 comes down. Dividing by 1 is really fun. And just like I said it would, the remainder is 0 again. So now I know that f of x equals 2x cubed plus 5x squared plus 8x plus 20 times, whoa, times x minus 1 squared. That was weird. I'm still muted here. I'm still muted here, right? I just heard my own voice through the microphone and I don't know why. That's weird. Okay. Scared the crap out of me, I'll tell you. Wasn't expecting to hear anyone's voice. I'm home alone and it's midnight, midnight. So, okay, I pulled 2 factors out and now Descartes' rule of signs says I am done looking for positive roots. I found 2, that's all there could be. Now I just need to look for a negative root and we'll wrap things up. So the possible roots remaining are just negative 1/2, negative 1, and negative 5/2. I'm hoping I don't have to work with fractions, so I'll plug in a negative 1. 2, 5, 8, 20. 2 comes down, negative 2, 3, negative 3, 5, negative 5. Nope, remainder is 15. F of 1 is 15. No such luck. Okay, we're almost there, folks. Let's try negative 5/2. Why not? 2, 5, 8, 20. So see, I'm not going with the original 5th degree. I'm just going with the 3rd degree that's left because I've got all the roots out of this part already. I just need to find roots in this part. So 2 comes down. Negative 2.5 times 2 is negative 5. That makes it 0. That's easy. 8 plus 0 is 8. Negative 2.5 times 8 is negative 20. And what do you know? We did it, folks. We found another root. Now I know that f of x equals 2x squared plus 8 times x plus 5/2 times x minus 1 squared. I'm going to do one thing before I finish the problem. I can finish with quadratics, but before I do, I'm going to donate a 2. See, this guy is all divisible by 2. So I can divide the 2 here and then immediately multiply the 2 here and solve 2 problems at once, a greatest common factor and a fraction. Factor out a 2 here and I get x squared plus 4. Factor in a 2 here and I get 2x plus 5. So the value hasn't changed. I've just shifted the 2 over. And now it's a little easier to work with. All right, x squared plus 4. If x squared plus 4 is 0, then x squared equals negative 4. So x is plus or minus the square root of negative 4, which is 2i. So I have my roots. And my roots are x equals plus or minus 2i. Notice those are conjugate zeros, so this is an application of the CZT. Positive 2i and negative 2i are conjugates. And then I've got negative 5 halves, or x equals 1. So here's our one negative root. We ended up with 2 positive roots, and it was a 1 multiplicity 2. And then the other 2 roots had to be complex numbers, and here they are. We did it, folks. That is all there is. That's the end of the unit. Thank you so much for joining me today. Such a relief to be done with that. All right, we're back on schedule, class. I will see you all next time I lecture. Probably going to be in a week or so.